Hi, welcome to the Signal Path. In this episode, I have another interesting product review for you guys. This is a Keithley 2281S, which is a precision DC power supply and battery simulator. You can see it's sitting on top of the 2280S, which is only the precision DC power supply. Now, I've been using this model for a long time, so I have a lot to talk about, and I've been using it for a variety of applications and experiments. So we're going to do a teardown, and we're going to look at all of its functions. There are a lot of cool things you can do with this, so let's get started. And here's the Keithley 2281S. Now it looks identical to the 2280S, which is a fantastic precision DC supply. You've seen it in the video. I've used it quite a few times in different experiments, but this one also has, of course, the battery similar function built into it. It does have the large LCD screen, fairly high resolution, very bright, and it does have a matte finish, which is great, but it does not have a touch screen like the SMUs and the recent multimeters that I have also reviewed. But they've done a fairly good job assigning these soft contextual buttons to the various menu items, so you can navigate the sophisticated GUI built into it using these buttons in still a reasonably good way. And the home and the menu buttons again bring you into various locations, as we will see inside the GUI. You have a USB port in the front, a hard power switch, which is great. We do have the plus and minus terminal and earth. There are no sense ports in the front of this unit. That's in the back. We'll take a look. And of course, a number pad, which is very useful as you would be entering a lot of numbers for various functions. You have a rotation knob. Unfortunately, no clicking on this one. And the output enabled as well. So it looks very nice, modern, is in line with the rest of the Keithley products. Quite happy with the form factor of this. Let's take a look at the back. One thing I do want to point out, that even though this unit doesn't have the touch screen, it is sharing the code base with the SMUs, and a lot of those functionalities are carried into this unit. And you can navigate it, as I said, reasonably well. So all the sophisticated triggering and plotting functions and setting advanced capabilities of the unit are carried over in the same GUI functions, which is great. So you get all of that benefits with this one. And here is the back of the unit. Of course, we have our fan as well as our AC input. We have a legacy GPIB port, and our outputs are available in the back as well. You can see two loops over here, which are the sense wires. So if you need to do 4-wire measurement, you can do it from the back of the unit. Now, this is pretty important for battery simulation because you don't want your wires, if they're long and have high resistance, to be part of the model of the battery or part of the behavior of the battery. So this way you can avoid that, and that's typical with any kind of power supply, but particularly important for battery simulation. Now, we also have this digital I/O in the back. Now, Keithley has some of the world's best hardware triggering and synchronization with SMUs and power supplies and multimeters, and that makes them suitable for production testing because time is really precious in production testing environments, and having these hardware capabilities that allows you to synchronize multiple instruments, make rapid measurements in an efficient way is critical, and they really do excel at that. We will see some of that during our testing. So after powering on the unit, in about 10 seconds, you get the main menu. Now, there are three main modes of operations this instrument supports. It, of course, can be a high precision power supply. It can also be a battery tester, which can charge and discharge the battery and create various battery models and measure ESR and other battery properties, which we will take a look at. And of course, the battery simulator, which you can use a battery model, either the one you generate yourself or some of the ones that are built in, to emulate the behavior of the battery across this discharge cycle. So we'll take a look at all of those. But what's really nice is that when you select one of these functions, and then you go under the main menu, you get all the functions for that particular mode of operation. And they're all fully independent. So advanced triggering, how you measure graphs and how you plot them, what kind of source and measure properties it has, are all fully independent from each other. So if I exit from this, and I go back to the main mode selection, and if I, for example, select the battery test now, and I go under the menu again, you can see that this is a different set of menus for that particular mode of operation, which is what you would expect, keeps them all separate from each other, and makes the GUI really easy to navigate. Again, a lot of thought has gone into creating this. So let's do a couple of experiments in each of these main modes of operation to understand what this instrument can do. And check out what's inside of this power supply. Now, this is officially the largest toroidal transformer I have seen in an instrument, at least of this size. It is absolutely massive and constitutes about 95% of the weight of this whole thing. Even has this own little handle that's epoxied in the center so that you can drop it in as you're working with it because it is so heavy, basically dropping it into its holding position. Now, you need something this size and of this quality, of course, not surprising from Keithley, to get the kind of performance you're getting from these kind of power supplies, and this is very common in their designs in general. Now, the instrument is broken up into multiple sections, as it often is for units of this class. We have a digital board, which has all the communication and all the interfaces. This is typically common between several classes of power supplies, and this is probably the same, and there's some hints on it as we will take a look. There's a little bit of a bodge wire on this one. And then we have a ribbon cable that goes from here to the front panel. Now, the front panel is a computer, a fully self-contained computer, which is where all the GUI runs and everything else. This is again a common architecture. Now this computer is not as sophisticated as the one that's on the source meters with a nice touch screen and so on, but it is running the same code base because it does have the same GUI elements and everything, which is nice to see in this power supply too. The only complaint I have at this view is that this ribbon cable that is sitting over here, it's a little bit close to this. It could potentially rub against this. Probably not an issue. This is not very sharp. Nonetheless, I would cover that. And other than that, I don't see anything that's an issue. Everything is nicely tied down. But we do have to see what's underneath over here. There's some protection circuits, which is a nice touch. I'll show you that as well. So first, let's get this thing off. So let's take a look at this digital board here. Now this board has clearly been designed to work with more than one product category because it can support up to 3 channels. It can control 3 analog channels of a power supply module. In this particular case, only one of them is being used. At the heart of it, we have this IMX25 application processor from NXP. Interestingly enough, this is an automotive grade product, or at least it could be depending on which part number you buy. So you may have some additional resiliency for temperature and power supply variation. It's surrounded by some memory. Here on the right side, we have an ST real-time clock chip here. Interestingly enough, it is backed up by 2 supercapacitors as opposed to a coin cell battery, which may be more common, but it may not need that. I wonder if the front panel has a separate battery for its own little display as well, as the source measure units definitely do. We have an NI part here. This is for GPIB and some associated buffers with it. Nothing unusual. There's an entire Cortex processor here as well. There's a lot of computation thrown into these boards. I guess it's just easy to design them that way. We have Ethernet and USB, and we have a chip particularly for the Ethernet controller. And as you can clearly see over here, we have a bunch of DC-DC converters and some power supply sections over there. These are low-profile capacitors because the space is somewhat limited. We have power going over here, and then we have a couple of connections that basically control the digital board. And the rest of it is really quite straightforward. On the other side, we go. Nothing really happening on this side. We have the connection to the LCD. We have the channel controller for the one channel we have here. You can see channel 1. But there's also channel 2 and channel 3. They're not populated, so there are some components that are obviously not needed. A small watch wire that we saw, more of the power supply control. Yeah, so this is a very nice, simple board here. Well, simple, relatively speaking, but this can control a lot of different power supplies. And just simply drop this in. And here's inside of the instrument itself. Of course, most of the volume is taken by this gigantic transformer and all the different taps that come out of it. And the circuit board itself is not very large, but there's a lot of functionality packed into it. And it's not very often that you find a precision reference inside a power supply. This is an LM399, I believe, which is binned. It has a different part number, but I think that's what's inside of this. And you need this because this, of course, has a 6.5-digit digitizer multimeter built into it. So not only does it do the emulation of the different kinds of batteries, and it's a power supply, it's also a precision instrument on top of that, which is very nice considering how small really the main PCB of this unit actually is. And a lot of that area is already taken by this heatsink. So there are a whole bunch of different precision resistors and whatever you need for building basically a multimeter on top of the power supply. We have a group of large capacitors here, a fairly large full bridge rectifier, which is also on a heatsink, and a lot of different devices on this main heatsink in the middle. Now this style of thermal management is also fairly common, where you have a fan over here directly pulling air through the heatsink. So there are fins in here which you cannot see from the angle, and that basically maintains this at a particular temperature that you want, and I'm sure there are temperature sensors monitoring it. And that removes a lot of the airflow from places you don't want it to be there. For example, underneath this, there are several big capacitors. These are also in the nice airflow path, which is great. Close them down and air probably comes down through this side and goes out. There's another transformer here powering perhaps a few other things. Now the compactness of this is impressive for the kind of functions you're getting. But remember that this heatsink doesn't need to be very large. With good design of the power supply and different taps that come out of the transformer itself, you can minimize the dissipation on this during operation as a power supply. This doesn't sink a lot of current into it, so when it wants to discharge a battery, it doesn't take a lot of current, so it doesn't need to dissipate a lot of power internally as a load, for instance. So this doesn't need to be very large. But overall, it's fairly quiet also when it runs, and the fan has a dynamic control, of course, on top of everything. And there are a lot of devices that are connected on the side of this. And here's the interface to the front panel, and you can see a couple of protection diodes as well as spark gaps in there so that it protects the rest of the device. It's nice to see. As always, of course, Keithley has excellent protection circuitry built in at the interface of their devices, whether it's the SMUs, the multimeters, or the power supplies. And here's some additional circuitry on this little board sitting behind the transformer, which I believe are responsible for the power and conditioning and so on of the line coming in, and there is a few additional protection circuits in there as well. Now this is most likely not a problem, but I did put some shrink tube on this little piece of metal, and then I routed the ribbon underneath it just for extra protection. So let's go ahead and try the power supply option. Now we have a 20 volt, 6 amp capable power supply with all the other benefit that comes with having a high precision instrument embedded in there. If I go under menu here, I can set things like the source behavior, the measurement characteristic, the graphing, advanced triggering, and everything else that you would expect to be able to adjust. Now under source over here, I have not just the voltage and the current, I also have delays as well as slew rate. Now I can change the slew rate both on the rising and on the falling, and being able to do that independently is important in some systems that are sensitive to how you bring them online and take them offline. Now we're going to leave those by default for now, but you also go under the measure menu, and here I can set things like the accuracy and the number of digits the power supply is operating. Now this is important because it changes the rate in which this power supply can sample. You can adjust the NLPC as well as the number of digits. You can go as low as 0.002, which gives you a very fast sampling so you can catch transient effects, as well as applying pulses to whatever you want to measure. We may try that later on, but for now we're going to leave it at 6.5 and 1, which is the highest resolution and lowest noise that you can have from this instrument, particularly with NLPC of 1. If you go higher, you may get a little bit better, but then there's diminishing return at some point. So let's do something a little bit unconventional with a power supply, taking advantage of its high resolution capability. Here I have a PCB, and there's a short circuit somewhere on this PCB. And that short is between the ground and power supply. It could be some internal node. And I'm going to use the power supply to find that. Now normally when you want to find a short, there's a lot of ways to do it, but you can measure the resistance and probe different areas. And as you get closer and closer to the point where the short is happening, the resistance will drop. But that change in the resistance is extremely small because you're looking at power supply planes, for example, and you may be talking about milliohms of difference, even smaller. And if you want to measure that tiny change in resistance, what you need to do is to put a lot of current through it, and that way measure the voltage across different locations, and from that you can interpret it. Or you can limit the voltage and then measure the current. So that's what we're going to do. Now the big advantage of limiting the voltage is that I can set the voltage of this power supply to 0.2 volts, which means that if I incorrectly probe something, the voltage is so small that I'm not going to damage anything. I'm not going to forward bias any of the junctions that could be there because the voltage is so low. But I do have 6.5 digit measurement capability on the current, so I can differentiate tiny changes of current, which corresponds to a very small change in resistance. So let's use that combination to see if we can hone in on the short circuit that's on this board. So let's give this a try. I also have a small rolling filter applied to this so we can stabilize the measurements a little bit. First thing I'm going to do is I'm going to short the two probes together over a piece of conductor so we can see the maximum current we can draw from the power supply, because remember there's finite resistance in these cables and of course finite resistance in the tips. Let's go ahead and try that. There we go. So you can see that we can draw currents as high as about 0.77, 0.775 amps, and that is basically when the two tips are touching. Now I'm going to move on to the two nodes that I know are shorter together. One is over here and one is over here. So there's a short circuit between these two. And you can see we're reading 0.544, 0.45 or so amps. And that's because there is an additional resistance. And that resistance is in the surface and all the traces inside of this PCB. So I'm going to go and probe the same 2 points, but I'm going to keep moving along the traces. And we can see if the current goes up or the current goes down, and that tells us whether we're getting closer to the short or further away from it. Okay, let's try that again. So here's the initial short, 0.53. Let's move a little bit further and see if that helps or hurts us. Let's go over here. That's on the same note. There you go. So now it's 0.514, and that means that we moved further away from it. So that wasn't good. Let's go back again to make sure. Yep, 0.55. That's okay. Let's go a little bit further down the line, see if we can make the short better, closer to the short. There you go, 0.59. That's good. That means we got a little bit closer to where our short was. We can continue going down, see if he helps us a little bit. 0.61, there you go, still getting closer. Let's go back here, 0.66, yep, getting a little bit closer. Over here, let's try this one. No, that's the wrong node. So that there's an example of something where I am probing the incorrect node, but because I'm only applying 0.25 volts, I'm drawing 8 milliamp, which is fine. That's not a problem then. So that's actually not the net we're looking for. We continue on. 0.7, there you go, that got a little bit better. We can continue down this route and see where it takes us. So I think we're very close to the node now. It's got to be around here. There we go, there it is. I think I found it. That's it. 0.87, that's the highest we have. So let's flip the board over and see if we can find where that short was, and there it is. That's actually the short that I added myself. There you go. So we slowly work their way towards this short by using the high resolution of this power supply. So let's do one more experiment with the power supply. Here I have a MOSFET and a power resistor. The gate of this MOSFET is controlled with the Tektronix AFG 31000 series arbitrary waveform generator. I'm going to use this to generate a pulse, and that pulse at the gate is going to open the channel of the MOSFET, allowing a large current to flow from the drain to source, which is provided by our power supply over here. Now that pulse can be fairly narrow, and of course the timing of the pulse may be unknown. So we want to configure the power supply to not only catch that pulse, but also trigger on it. We can talk about some of the triggering capability and measurement speed of the unit at the same time. So let's go ahead and set up our instrument for this kind of measurement. Now we go into the menu here. First thing is to change under the measurement menu is the NLPC. Now I'm going to change that to its lowest possible value, which is 0.002, which will give us a lot faster measurement at the cost of some noise, which is okay because we're trying to capture a very narrow pulse here. 0.002. I'm going to enter that. Now here I've left the number of digits to 6.5. You can also change that to 4.5. It will give you a little bit more as well. Let's exit that. Now let's go under the buffer menu here. Under the buffer menu, I'm going to change the size of our buffer to be 250 samples. It can go as high as 2500. So here's 250. And I'm going to leave the buffer filled to always, meaning that it's going to treat the entire buffer as a circular buffer. So as soon as it fills up, it begins to fill it from the very beginning. I'm going to leave all the statistical functions to be applied as default and the auto zero and everything as well. And here is where you can export it to a USB if you want to. Now let's go ahead to the actual graphing menu over here. And under the graphing menu, I'm going to change the graph to only show the current because I'm not interested in the voltage. The voltage is going to be constant in our case. It's going to be 5 volts that I'm setting myself. Let's go ahead and show only the current. Perfect. I'm going to leave everything else as well. We're going to have the auto adjustments on the vertical axis. You can manually adjust that, but the instrument is in auto scale anyway. Let's go out of that. And then we're going to go on to the level trigger. So here's where I'm going to set the instrument to trigger in the event of either a voltage or a current change, either in the positive or the rising or the falling edge, kind of like an oscilloscope essentially, which is very convenient. So let's go ahead and say I do want to trigger on the current. Now note how you can have both of these at the same time, which is quite nice. And let's go down over here, change the current. Let's say trigger on whenever we hit 250 milliamps. And on the rising edge, since the pulse is going to be a positive pulse. Okay, we're going to keep that too. That's set up. And then finally, we're going to go under the trigger menu and adjust the trigger. Now I'm not going to actually make any changes to this, but it's important to note a very useful feature. There is, in this power supply mode, the trigger count is default as 1, but you can change that in the other modes. But you have an arm count and a trigger count and a sample count. This allows you a very wide range of flexibility on how the instrument captures data. So if you have some conditions where you want, for example, the instrument to ignore and then only then begin to make measurements, you can do that with a combination of adjusting the arm, trigger, and sample count, which can be quite handy. And this is expected as Keithley has very good triggering options on their instruments. Let's go back. There was one thing I actually forgot to do. The data before the trigger from 0 to something larger. This is the amount of data that's going to be shown on the display before the actual waveform begins. And that's important, just like an oscilloscope. When you want to move the triggering point, have some pre-triggered data essentially. Let's go over the opposite over here and change that to 25, which is 10% of the total number of samples we're capturing. Okay, I think we're ready. Exit at that. Let's set the power supply to 5 volts. Let's set the current limit to 5 amps. And let's give it a pulse. Okay, so the power supply is enabled and you can see we're drawing no current because the pulses are manually triggered. I can press the button on the Tektronix AFG series and it will generate the pulse. Now I can do that. I'm going to do it, a couple of times a second, and every once in a while you can see we will catch a bit of current, but of course that's not good enough to characterize this. So let's go ahead and clear the buffer. Okay, and let's look at the graph. So here's the graph as it's being generated. You can see that we have 250 samples over here. We're drawing no current here. This is all in amps, so it's a tiny amount of just residual current and noise that's being measured. I'm going to go ahead and trigger the pulse once. Now as soon as I do that, the trigger is going to get activated and the sampling is going to stop. Now it's nice because it's rolling constantly until I actually apply the trigger. Here we go. I'm going to apply the pulse. Here's our pulse. And there it is. Look at that. It measured the pulse perfectly. You can see the pulse went as high as 0.3 amps, and you can see the maximum value calculated here. Now one thing I wish they did is that not set the background of this to be gray. I don't know why the background isn't just black. It just makes it a little bit harder to see, as you can clearly see from the camera as well. But you can measure all kind of statistics here at the bottom. So let's make the pulse a little bit narrower. So I'm going to change that under arbitrary waveform generator. Okay, the pulse is narrower now. You're going to go over here. I'm going to clear the buffer one more time and view the graph again. I'm going to apply the pulse once more. There it is. So here's our narrower pulse. This is kind of at the limit, basically, of what we can measure. And of course, if you make it smaller, you may not necessarily catch the full amplitude. But you can see we're still going to the maximum amount of current again. And we have the 250 samples. So this is, of course, a 10 millisecond pulse. I just wanted to make sure I mentioned that before I forget. Let me try half of that and see if we can capture that one too, just out of curiosity here. Here's the graph. Let's apply the pulse. There you go. Oh no, actually, you know what? It caught that too. Even though this is now even smaller, this is 5 milliseconds now. So yeah, it's pretty good. Its sample rate definitely can catch very narrow pulses, which is good for these switching power supply applications. Now keep in mind that you can also apply any kind of steps and ramps and all kind of different voltages too. You can control the way the instrument generates a list of voltages. So you can stress test a variety of different kind of DC-DC converters or loads that you want to try out. I'm not going to go into the details of that for the interest of time, but keep in mind that all the voltage and ramp creation capability is also built into the unit. So now let's talk about the battery test capability of the unit. So we can go under that, and then if you go under menu, we're going to get the unique menus associated with that function. Now under the source here, we have the charge and discharge menu. Now there is a limitation here that you need to keep in mind. Now this instrument is a 2-quadrant instrument. It can source current and sink current. Even though it's 2-quadrant, it doesn't sink current in the same way as an SMU does. The discharge limit is actually fixed to minus 1.25 amp and it's not adjustable. It means that if you want to discharge a battery using this instrument, it will discharge it at this current, whether the battery can do it or not. That means that if your battery is not able to provide that much current, you have to put an external series resistor. Now, of course, once you put the resistor, you cannot calculate the battery capacity anymore. Therefore, this instrument calculates battery capacity only during a charge cycle, and more importantly, can only create a battery model during a charge cycle. This has some limitations, of course, because if you want to create a battery model, for example, for something that's not rechargeable, you cannot do that with this instrument because the instrument does not create a model during the discharge, and because of this limitation, of course. Now, this is a little bit of an inconvenience, but it does have a trick up its sleeve. It can use an SMU if you have one, use the model generated by the SMU with a custom script, and you can put that back into the unit, and that can then be a discharge model. So we'll take a look at that separately, of course, but something to keep in mind when you want to charge or discharge a battery. There are a variety of battery performance parameters the instrument can measure, and we can set some of those characteristics over here under this menu. Now the unit can also measure supercapacitors, and I've already set that up, so let's see how that's done. So I have set the maximum voltage of the supercapacitor here, which is 5 volts, and the current limit to be 0.5 amp. So that's how much current is going to apply to the supercapacitor. But I've also indicated 2 interval voltages, a low and a high one, 3 volts and 4 volts. So what the instrument will do is that it will try to charge this capacitor at a constant current, and once it crosses this threshold, it begins to measure how long it takes until getting to the second threshold. And it's going to use a linear equation because we're pushing constant current into the capacitor, and it's going to try and calculate the capacitance based on that. Now I've already connected the capacitor here, some mystery capacitor, and I'm using a 4-wire Kelvin measurement connected to the back of the unit. So we do have the resistances account for. So let's go back to the main menu here, over here, and I'm going to enable the measure capacitance and see what happens. There we go. So as soon as we turn that on, we can see that we have 0.5 amp going into the capacitor. The voltage of the capacitor is building up. That's going to take a little bit of time until it hits 3 volts, and once it crosses that, it's going to begin computing capacitance. There we go, almost there. There it is. So it is beginning to calculate. So it's going roughly through that. So it's estimating it as the slope, essentially. Let's keep going and see what happens. It's going to hit 4 volts any moment now. And then it's going to stop. There it is. So it's calculating the capacitance to be 5.5 farads. And if you look at this, let me disconnect this. And over here, and this is indeed a 5 farad capacitor. And normally these things do rate a little bit higher. This is made of 2 capacitors in series, as you can see, each of them being 5 farad, but each of them are only 2.5 volts. So you can use that very easily to measure very large capacitances. Now these capacitors are very common nowadays because they have a very low ESR, as well as being able to be charged and discharged very rapidly. So a useful feature to have. So let's use the instrument to measure the equivalent series resistance of this LiPo battery. This is an 18650 cell connected again to the back of the unit. I'm going to put it here on the side. We're going to go under this menu over here, VOC ESR, And here we have a couple of options. We can change the delay, and that's how long the instrument is going to take before making a measurement. But more importantly, the instrument is going to do that all internally for you. So first, it will measure the open circuit voltage of the battery, and it's going to apply a delta voltage offset away from that and measure the amount of current the battery is going to take. And from that, it can estimate the equivalent series resistance. Let's go and try that. I'm going to go measure. There we go. So you can see that the battery is actually almost fully charged, 4.14 volts, and the ESR is 0.37 ohms, which is typical for this kind of battery. I can measure it again, and I reckon it changes a little bit here and there, but it essentially stays the same. But I want to double check to make sure that this number is correct. So let's go ahead and modify the battery and make it worse and see if this ESR follows through. So I made the battery a little bit worse by adding a series resistor to its output, a resistance of exactly 1 ohm. So we're going to measure the ESR before and after the resistor, and we expect a 1 ohm degradation. So here's before it. You can see I'm measuring 0.42 ohms. I'm going to move the positive terminal to after the resistor. I'm going to repeat the measurement. And check it out, we're exactly 1 ohm worse. So indeed the battery is performing as expected, and the instrument is able to capture the equivalent series resistance. So I'm going to go ahead and discharge this battery down to 3 volts so that we can recharge it and create a model out of it. So I'm going to go ahead and exit here. I've already entered all the parameters. I'm going to turn this on. And you can see that I'm drawing the fixed amount of current from this. And it's going to build an amp hour model of this battery. It was almost fully charged anyway. We're going to wait until this reaches the 3 volt limit, and in that case we can then recharge it and measure its full capacity and create a model out of it. So after discharging that single 18650 battery, I thought it would be interesting to charge a different battery, something that has 2 18650s built into it and some battery protection on top of it, so we can see what happens. I charged it at 2 amps, which is a rated value. You can actually charge it even faster if you wanted to. But in this case, you can see that the instrument has returned the total capacity at almost 2.4 amp hour, which is a little bit better than what it's supposed to be. And remember, this is the charging behavior of the battery, not the discharge. Now, once you've done that, you can generate a model. Once you press that, it'll ask you some basic questions. The minimum battery voltage is correct, and the maximum is also correct. And we can put it into any of the memory slots we want. Let's put it into 3, for example. That's it. So now that model is stored inside of the instrument. Now I go back over here, and if I go over onto the graphs, you can also see the exact graph of the battery and how it behaved during its charge cycle. Now keep in mind that I use the charging cycle to generate this model, which is fine for a lot of cases, but I'm interested to also using an SMU at 2450 to create a discharge model of the battery, which can be more beneficial in other scenarios. So let's go ahead and do that so we can use this instrument then in its emulator mode. So let's go ahead and use the Keithley 2450 to create a discharge model of a battery that we can use in the battery simulator. Now I've chosen a much smaller battery, this one over here. This is actually only a 0.67 watt hour battery. I'm going to use this to run some portable device, and we want to find an exact discharge model of this. Now I already have the script for that loaded onto this USB. I'm going to connect it using a 4-wire measurement in the front panel and go through the script so we can measure the capacity and create a model. Okay, let's go ahead and load the script. I've already put it on a USB stick. There we go. So it's going to give me a warning about being careful with lithium-ion batteries, which of course we know. We're going to use the front terminals. And we're going to use 4-wire measurement. And it just did an open circuit voltage measurement of the battery, 4.22 volts, so the battery is fully charged. It's satisfied with that. So now we're going to characterize how we want to discharge this battery. Let's give it a name. Let's just call it battery. And we're going to do a constant current discharge. I'm going to do a constant current fairly aggressively at 0.2 amps. This is 180 milliamp hour, so we're really charging it at almost full capacity, just a little bit over. And we're going to see how low we want this to discharge to. Again, we're going to go somewhat aggressively. Let's go down to 2.75 volts. And we're going to measure ESR every 2 seconds. That's perfectly fine. So it's now going to ask me to continue. And it's going to start. There it is. So it's going to discharge slowly at the specified current of 200 milliamp. You can see that it constantly measures the open circuit voltage and it constantly measures the ESR. So we're going to allow this to run through and discharge the battery. We can monitor the progress here, and we can see the discharge curve as well. So we're going to have to wait now until this is fully discharged so we can grab the model and bring it into the battery emulator. And it is finished. It took just under an hour to do this, and you can see that the battery degrades very quickly at the very end once it reaches the voltages below 3 volts, as to be expected. This is how these batteries are supposed to behave. So now we've saved the model onto the USB. We can take it into the battery simulator. And I went ahead and I loaded the battery model directly into the emulator from the 2450. It's a pretty straightforward process because it's just a .csv file, and this instrument knows how to interpret that. Now once you do this and you're in the battery emulator mode, you're going to get some pretty useful set of information. First of all, you see the kind of a visualization of the battery capacity here on the left. You can see the battery measurement has been done at 198 milliamp hour. That's roughly correct. That's the capacity of that battery, and the ESR is 0.361 ohms. Now the state of charge is at 100%, meaning that right now the emulator is going to behave as if the battery is fully charged, and it's going to drain it slowly depending on how much current you take from it, which is quite handy. And on the right side, we have the open circuit voltage of the battery and the terminal voltage of the battery, which are essentially the same right now because there is no load under the battery and the output is not enabled. Now, another very useful thing you can do is you can set the limit on how much current this instrument gives you from the battery emulation mode. Now, when you have a real battery, if you short circuit it, you could potentially damage something, or if your device under test is taking too much current, it may not be good for the device under test. You may want to protect that. You can actually limit that over here. And there are also over circuit protections and other kind of voltage protections you can do on top of this. So let's go and enable this battery emulation now. Now when we turn it on, you can see there is a tiny difference in current, and that's going to jump up and down a little bit. That's because even though the cell phone over here is turned off and it is connected directly to the output, it is going to draw a little bit of current because it's in standby mode and it needs to detect when the power button is pressed. So I'm going to go ahead and turn the cell phone on. It's a pretty old cell phone. There we go. Now as soon as we turn it on, we can see that we have a positive current coming out of the emulator, and this current is going to change quite a bit as the device is going to boot. And if you look at the very top of this, you can see a blue region. I don't really like the color scheme of this. I think they should make the colors a little bit more contrasting from each other. But that blue region at the top is a difference between the open circuit voltage and the terminal voltage. And that's going to be a function of how much current you're taking from the battery and the ESR of the battery. And that's why it's pretty important. There you go, the cell phone has now fully loaded. It's looking for service and it's drawing about 250, 270 milliamp. Now you should also note that this battery is draining pretty fast. And that's because this is a tiny battery, not intended for use for the cell phone. The cell phone is not going to last a very long time using this kind of battery. I have also set the screen brightness and everything to be the maximum to really drain it quickly. Now this is in dynamic mode, meaning that the battery is going to continue to drain as if it is connected to the cell phone. As far as the cell phone is concerned, this cell phone cannot tell that this is not the lithium-ion battery that is supposed to be connected to it, so it's going through all the process as if a real battery is connected. So we can set the battery operation into distinct modes. We can set it into dynamic mode, which is what it is set to right now, and it means that it's going to drain the battery depending on the current. You can also set it to a static mode. In the static mode, you can keep the battery at a particular state of charge level permanently, and depending on how the device obviously behaves, is going to get a different open circuit and terminal voltages on the battery. This is a crucial behavior of the battery emulator because it means that you can keep your battery state, let's say, near fully discharged and find out how the circuit operates, which we will take a look at later on. But let's back this to dynamic mode over here, and let's change the state of charge to somewhere in the middle of the battery's operation, let's say 50%. Okay, so as soon as you do this, you can see that the battery is now 50% depleted, the open circuit voltage degrades as well, and there's some change in the ESR. Everything is still working out perfectly fine. But now look what happens when I plug the battery into a charger. I have a USB port over here, which I can connect into a charger. Here we go. And as soon as I do that, check out what happens. We get the reverse operation. Now the cell phone is taking battery, and you can see the status here has changed, and it's telling us the battery is now being charged. Now the maximum current you can charge the battery is set to the maximum current this guy can accept, which is 1.25 amps. But this is a very large amount of current, so you can charge a lot of different batteries using that system, and this is why it's so important for this instrument to be 2-quadrant, even though it does have that limitation of the maximum current. I also created a second model where I artificially increased the ESR in the .csv file generated by 2450 to make the battery seem a lot worse. So we can load that and see what that looks like. This is a battery good model. I have a battery bad model. Press enter on that. So now the ESR is 1.8 ohms. And look at the big difference that you see between the terminal voltage of the battery and the open circuit voltage of the battery. And if you look carefully, sometimes you can see that the screen will flicker ever so slightly. And that's because the DC-DC converters in here are rapidly servicing different parts of the cell phone. So there's a big change in the current. And the big change in the current in here means a huge difference between the open circuit voltage and the terminal voltage of the battery. This is why it's so important to have a low ESR for a battery so that DC-DC converters can take the most out of it. Now remember that the capacity of this battery hasn't changed. Of course, you can't take all the capacity out anymore because some of it will be dissipated on the ESR, but that's an example of why it would be so important to have a good ESR battery. Let's go back onto the good battery again. There we go. And let's try one other thing. Let's take the charge really down. Let's take this state of the charge, bring it down to, let's say, 20%. Let's see if this cell phone survives that. There we go. So it's now really low. Seems to be still somewhat okay with it. Now let's load the bad battery and see what happens. Okay, here's the bad battery. Alright, we're going to set the state of the charge of the bad battery also to 20%. There we go. This is not going to be good for it. You can see that the terminal voltage is now 2.7 volts, and there you go, the cell phone just died. So it was exactly the same state of charge, but the two different battery models can completely react differently to DC-DC converters. Now, this is a double problem in reality, because when the terminal voltage of the battery goes down, the DC-DC converter will demand more current, making the situation even worse, because it has to deliver a fixed amount of output power into the cell phone's processor and other functions it has. So when you start to discharge a battery, at the same time you want more current from it than you did earlier. So that's really a big problem for generally battery powered devices that have DC-DC converters in them. And you get all the benefits of the plotting functions that it comes with. So if you go on to the actual plot functions of the battery here, you can plot the different behavior of how much current is being taken, what the state of the charge of the battery is, how it's discharging, how much capacity is being used. Pretty useful to have a good digitizer on top of the battery emulator, and you can gather that data, take it out, plot it, analyze it, and so on. And there you have it. I hope you enjoyed this detailed review of the Keithley 2281S precision supply and battery simulator. Now, it is a fantastic instrument. I find myself returning to it quite often because of its high precision and high output power in power supply mode in particular. But of course, the battery simulator is a huge plus, and you cannot be developing any battery powered device without having something like this in the lab, because it helps you push the boundaries of these DC-DC converters and ensure that your product operates across a wide range of battery conditions, and especially if you take aging into account. Really, the only limitation it has is in the battery test mode, where the discharge model cannot be used to create an actual battery model. You have to use a charge model, and then the current sink is fixed to a maximum of 1 amp. Aside from that, I really enjoyed using it, and I think that it's a fantastic GUI design into it and all the nice things that comes with the software that Keithley has developed. It is also compatible with Kickstarter software, which I have shown many times on the channel, so I didn't go into it in this particular video, but of course you can as well do that. Let me know what you think in the comment section. As always, I don't get any benefit from the sales of these units, and all the links that I provide are direct links to the manufacturer. But of course, if you ever do purchase one of these, let them know that you watched this video. It would help me bring more of these kind of contents for you in the future. As always, I'll see you in the comment section.